This video is for question 12 from the homework, so it's really important that you actually are looking at that question because it probably won't make much sense. The video won't make much sense without it. So what it says is that the table below shows the average distance of each of the 9 planets from the Sun and the length of the year in Earth years. And for part A it says to plot the length of the year against the distance from the Sun. Describe the shape of your plot. Now some people are still saying, well, I don't know which one's going to be the explanatory variable and which one's going to be response. We're looking at it in terms of X and Y, it's more difficult. But if you look at it in terms of explanatory and response, or if you just go down and read the rest of the question, it might give you a little insight. The next part of the question says to re-express one or both variables to straighten the plot. And it says to use the re-expressed data to create a model describing the length of a planet's years based on its distance. And I think you would probably say that the distance would explain the length of the year. So distance is going to be X, where length of the year in Earth years is going to be Y. And that's the way I've set up this problem. And so again, think about explanatory and response, but also read the rest of the question to see what model they're looking for, and then just work from there. So I've put this data into list 1 and list 2, and when I graph it, what I see is this is, I don't know, possibly linear, but it looks like it's more positively curved upward. So it looks like it is a positive association, but it does look like it's slightly curved, okay, upward. Just to make sure, the best way to check to see if a linear model is appropriate is to graph the residuals. In order to do that, we first have to run our linear regression. If we don't, it's not going to calculate the new residuals. The residuals we find will be from some other problem, and that could be a problem. So we're going to run a linear regression. We're wanting to use list 1 and list 2, so by default we don't have to put anything in here. We hit enter. So that would be our linear model, but when we go to stat, edit, and we head over to list 3, and we put in our residuals, and when we go to stat plot, and we graph those against list 1, list 3, what we get is we definitely have a curved shape. So this is not appropriate. Remember, the residuals, we definitely don't want any sort of curve. We want them kind of equal scatter, nothing interesting, no curved shape. So we know that's not appropriate, so we need to re-express either one or both of the variables, is what the question says. So we're going to go back to stat, curved upward, we'll go to edit. Then I'm going to overwrite my residuals because they don't mean anything for this particular problem, because they just show the model's not appropriate. So for list 3, the first thing that I will do is I'll take the square root. So I'm going to take the square root of list 2, and I'm going to put that here. And then I'm also going to take the log of list 2, which is y, common log. You could use natural log if you wanted, of list 2, and I'm going to put that here. So now I'm going to take a look at these two scatter plots. So 1 against 3, this is going to be x versus the square root of y. So I hit graph, and I go to zoom 9. Now, to be honest, I don't know that I'm even going to look at the log, because first it looked like it was curved upward, now it looks like it's curved downward. So then the proper re-expression is probably somewhere in between. So what I'll do is I'll refer you to page 231, below the blue box, where it says, when we try to model the relationship between the length of fishing line and its strength, we were torn between the -1 power and the -1/2. Well, in this case, we're not stuck between those two particular powers. We are stuck between 1/2 and 0. But again, we're stuck between, not 1/2 and 0, we're stuck between 1 and 1/2. So it says the first shows slight upward curvature and the second downward. Maybe there's a better power between those values. It says the scatter plot shows what happens when we graph the logarithm of length against the logarithm of strength. So they're taking the logarithm of both x and y. So that's what we're going to do. Because what we saw is that we needed a re-expression, a power of re-expression somewhere in this ladder in between our values. So what I'm going to do, I'm going to go to stat, I'm going to go to edit, come over here to list 3, and I'm going to take the log of x, which is list 1, enter, make sure you hit enter, and list 4, that was a log of y, that was already there, but just to make sure, a log of list 2, yep, we have that. Now let's take a look at this plot. stat plot. Now we need to do list 3 versus list 4. Oop. Let me go back up here for a second. List 4. Now we grab zoom 9. Now that's nice and straight. So that's probably the re-expression we need to go with, and that is the one we're going to go with. So now, actually before we go with this model, we probably want to run the regression and then take a look at the graph of the residuals. So we'll go to Stat, Calc, linreg. Now because we're using list 3 and list 4, we need to specify. So list 3, comma, list 4. So there's our model. Our residuals have now been calculated. So when we go to Stat, Edit, let's come over here to list 5, second list. Let's bring our residuals in. Graph, stat plot, list 3 this time versus list 5, second L5. So now when we graph zoom stat, there we go. That's what we're looking for. So the linear model we now know is appropriate. Let's go back and take a look at R and R squared. We've straightened it out. We know that both X and Y are in terms of the log of X and the log of Y. So let's go back here and let's find this model now. So calc, again, linear regression, second L3, comma, L4. And the R and the R square valued are extremely strong. Here we have our model. Just pay close attention to the order. We have the y-intercept and then the slope. We have an R squared of almost 100%. So 100% of the variation in y is accounted for the variation in x. When you see something like this, it almost seems like this has to be some sort of law, that it's this perfect, that it's this close, that, again, in reality, this doesn't usually happen unless there is something bigger that we're not aware of kind of governing this behavior. So it is quite possibly a law, but it's neither here nor there. So for this question, then, our model would be the log of length hat, that's the length of the year in terms of Earth years, is equal to approximately negative 2.96 plus 1.5 times the log of the distance. Alright, that was part B. We've already kind of described part A. And if you go back here and you take a look, negative 2.96, 1.5. So there's our model. And for part C, it says comment on how well your model fits the data. Well, according to the graph of the residuals, the model fits very well, or at least, I'm sorry, is appropriate. And given that R squared is almost 100%, the model fits the data extremely well. So the R squared of 100% approximately means that the data fits well. The graph of the residuals, showing no curved pattern, nothing interesting at all, means that the model, linear model, is appropriate. And so that's how you would answer question 12. You probably see something like that tomorrow at the beginning of class. So make sure you understand the ladder and all your powers and what happens if on that ladder you fall in between rungs. You want to take the log of both X and Y and see if that straightens it out. So that's how you answer question 12 from the homework.